The European Space Agency (ESA) has released a new collection of highly anticipated images of the interstellar comet 3I/Atlas, captured as the mysterious object made its closest approach to the planet Mars last week. These observations, obtained by the ESA's ExoMars Trace Gas Orbiter, have generated significant excitement among astronomers worldwide, not only because they offer a rare opportunity to study an interstellar visitor passing near a neighboring planet, but also because they highlight the unique scientific challenges involved in observing such an unusual and fast-moving object traveling through our solar system. The freshly revealed images portray the comet as a dim, fuzzy point of light, an appearance similar to images captured by NASA's Hubble Space Telescope earlier this year, though the ESA spacecraft was positioned at a much closer range during its observations. Despite this proximity, the comet's nucleus remained unresolved due to its small size and the limited resolution available at such enormous distances, reminding researchers of the inherent difficulty in studying interstellar objects that are both faint and rapidly evolving. Although the primary images have now been released, ESA scientists noted that additional data may also have been collected by one or more of the agency's spacecraft during the close passage. In particular, researchers are still analyzing data from both the ExoMars orbiter and its companion spacecraft, the Mars Express orbiter, to determine whether either was able to gather spectrographic information during the event. Such data could be crucial, as spectrographic readings allow scientists to perform chemical analyses of a comet's emissions, potentially revealing details about its composition, behavior, and physical structure. However, ESA stated that it remains unclear whether such valuable spectral measurements were successfully recorded due to the challenging observational conditions. Despite this uncertainty, the possibility of capturing chemical signatures from an interstellar comet represents an extraordinary scientific opportunity, one that could help astronomers better understand not only this particular object, but also the broader category of celestial bodies that originate beyond our solar system. The comet, officially designated 3I/Atlas, was first detected in early July and immediately drew the attention of the global astronomy community for a variety of reasons. Only the third confirmed interstellar comet ever observed, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. 3I/Atlas stands out due to its remarkable size, unusual behavior, and the velocity at which it is traveling. Many of its characteristics differ significantly from those of comets formed within our solar system. This includes the nature of its coma, the cloud of dust and gas surrounding its nucleus, as well as its patterns of outgassing, its directional behavior, and its brightness fluctuations. Such traits have led scientists to consider that 3I/Atlas may belong to an entirely different class of cometary objects, or may have experienced a formative process in an environment radically unlike that of our own solar system. Each interstellar visitor offers a rare chance to study materials and processes that originated around another star, possibly even in another planetary system, thereby expanding our understanding of planetary formation and cosmic evolution. As the comet approached Mars last week, ESA scientists directed the cameras aboard both ExoMars and the Mars Express orbiter toward the object, in hopes of capturing detailed imagery. Unfortunately, Mars Express faced limitations because it operates with shorter exposure times optimized for imaging the Martian surface. It was not able to acquire any clear images of such a faint and distant target. Interstellar comets are extremely dim, and the rapid transit of 3I/Atlas through space made long exposures essential for capturing useful data. Without the ability to extend exposure durations, Mars Express was effectively unable to detect the object, leaving ExoMars as ESA's primary imaging tool during the flyby. The ExoMars orbiter, however, is equipped with a sophisticated imaging device, the Color and Stereo Surface Imaging System, commonly known as CASIS. This camera was originally designed to capture high-resolution images of the Martian surface, producing detailed color and stereo views that help researchers analyze geological features. Its impressive technical capabilities include a resolution of 11.36 microradians per pixel, which translates to approximately 2.34 arcseconds per pixel, At a distance of 30 million kilometers, the approximate range at which the comet was observed. This imaging precision corresponds to about 340 kilometers per pixel. While this level of resolution is extraordinary for mapping planetary surfaces, it exceeds the expected diameter of the comet's nucleus, which scientists estimate to be somewhere between 5 and 46 kilometers. As a result, the nucleus of 3I/Atlas is far too small to be resolved directly, appearing instead as a pinpoint of light surrounded by a diffuse, hazy glow formed by the comet's expanding coma. The fact that the comet appears fuzzy and unresolved in the images is not a limitation of the camera itself, but rather a reflection of the physics governing cometary behavior. As comets approach the sun, solar radiation heats their icy surfaces, causing volatile materials to vaporize and stream away from the nucleus. This process creates the coma, a cloud of gas and dust that surrounds the solid core and scatters sunlight, making the comet appear brighter, but also more diffuse. In the case of 3I/Atlas, the coma has grown significantly as the comet continues its inward journey. As the object draws closer to the sun, its behavior becomes more dynamic, and the release of material increases. This makes it more challenging to discern the physical shape or surface structure of the nucleus, especially at extreme distances. Nick Thomas, the principal investigator for the CASIS camera, emphasized the difficulty of the observation in a statement released by ESA. He noted that the comet is between 10,000 and 100,000 times fainter than the spacecraft's typical targets, meaning that even with long exposure times and advanced imaging techniques, acquiring usable data required exceptional precision. The fact that CASIS succeeded at all in capturing the object demonstrates the instrument's impressive sensitivity and the expertise of the mission team that planned the observation. Data from previous observations provides additional insights into the comet's physical properties. Measurements based on non-gravitational acceleration, small deviations in the comet's motion caused by the uneven release of gas and dust, indicate that the nucleus must be at least 5 kilometers in diameter. However, earlier observations by NASA's SPHEREX mission suggest it could be much larger, possibly up to 46 kilometers across. If confirmed, this would make 3I/Atlas significantly larger than either of the previous interstellar comets, giving scientists a uniquely massive example to study. SPHEREX data also suggests that the comet is releasing a substantial amount of carbon dioxide, forming an enormous CO2 plume extending approximately 348,000 kilometers into space. This plume is far too large for CASIS to detect at its current distance, but its presence underscores the powerful and unusual outgassing activity occurring within the comet. The brightness of the comet, combined with the size of its coma and gas plume, raises intriguing questions about its composition and history. Interstellar objects are believed to be fragments of distant planetary systems, pieces of ice, rock, or dust ejected into interstellar space by gravitational interactions, stellar evolution, or collisions. Over time, they wander through the galaxy until they eventually pass through another star system, as 3I/Atlas is now doing. Studying such objects provides a way to sample materials that formed under entirely different cosmic conditions than those in our own solar system. Differences in chemical makeup, isotopic ratios, or physical structure could reveal important clues about how planets form around other stars, how cometary bodies evolve over long periods of time, and what role such objects may play in transporting organic materials across star systems. The flyby past Mars represented a rare alignment of timing and positioning that allowed multiple spacecraft to observe an interstellar object at the same moment. Although the limitations of resolution and exposure time prevented researchers from resolving the comet's nucleus, the collected data still offers valuable insights. Every observation contributes to a growing body of knowledge about interstellar comets, objects that are notoriously difficult to study due to their speed, brightness, and unpredictable behavior. As 3I/Atlas continues its rapid passage through our solar system, scientists from ESA, NASA, and other institutions will continue to monitor its activity using both space-based and ground-based telescopes. The release of these new images marks an important milestone in the study of interstellar objects. Even though the comet appears only as a faint, fuzzy point in the ExoMars imagery, the significance of capturing such a rare and distant visitor cannot be overstated. Each new interstellar discovery broadens our understanding of the universe and offers a glimpse into the processes shaping planetary systems far beyond our own. The challenges described by the ESA, the faintness of the object, the limitations of spacecraft exposure settings, and the difficulties in resolving a tiny nucleus millions of kilometers away, highlight the extraordinary precision required for modern astronomical observation. Yet despite these challenges, the successful imaging of 3I/Atlas stands as a testament to human ingenuity and the relentless pursuit of scientific exploration.